All right, here is a problem from your review. I kind of thought I would look at a few of the questions on your review packet and help you out because we're not gonna have a lot of time to review. So I thought I'd make a video so that you could get help with these questions in a different way. So here's number 8 from your packet. All right, it says the accompanying figure shows the velocity v equals f of t of a particle moving along a coordinate line. So this is the figure, this is the velocity graph that they gave us. And they ask us some questions about it. So looking at the velocity graph, we have to determine A, when does the particle move forward, backward, speed up, slow down? Okay, so this is kind of a tricky question if you haven't done it in a while. Velocity is directional. So where does this particle move forward? Essentially, I'm looking for where v is positive. Backwards, where is the velocity negative? All right, speed up is when velocity and acceleration are either both positive or both negative. So we'll look at that in a second, and there's a way to tell that by looking at the graph. And then slow down is when velocity and acceleration are opposite. So like meaning if velocity is positive and acceleration is negative, that would slow the particle down. Also, if velocity is negative and acceleration is positive, that would slow the particle down. So first thing is, where does this particle above the x-axis? Since this is the velocity graph, and I'm just looking at where it's above the x-axis. So when does it move forward? From 0 to 1, and then again from 5 to 7. All right, so if you just kind of look at it as in terms of velocity being directional, I'm just looking at where this thing is above the x-axis. The next question, where does it move backward? It will be on the other part, so 1 to 5. And actually from 7 to 9, if you look over here, it's really not doing anything. It's just kind of sitting, so it's not moving forward or backwards, so that would be nothing at that point. Where does the particle speed up? So this is a good question. So where is the velocity and acceleration both positive or both negative? So right here, I know the acceleration is negative, and you might be asking how. Well, if I'm looking at the velocity graph, since acceleration is the derivative of velocity, I'm thinking about the slope of the velocity graph when I'm trying to determine acceleration. So where does it speed up? Right here, this is velocity negative, and acceleration is negative. Therefore, it's speeding up from 1 to 2. All right, so that's a little bit tricky, but you got to look at when the forces are acting together. Once again, from here to here is when you get that same situation, but now velocity is positive and acceleration is positive. When both forces act together, that speeds the particle up. So this would be speeding up from 1 to 2, and then in union with 5 to 6. All right, slowing down is when the forces act in opposite ways. So here, velocity is positive, but acceleration is negative because it's a negative slope. Same thing here. Velocity is positive. I'm sorry, velocity is negative, but acceleration is positive. So opposing forces. And then once again, from here to here, velocity is positive, but acceleration is negative because the slope is negative. All right, so then I would write slowing down from 0 to 1 in union with 3 to 5, and then in union with 6 to 7. All right, so that was the trickiest one. And if you get through that problem, the rest of these go kind of quick. So now, where's the particle's acceleration? Positive, negative, 0. So this is, again, we're looking at slope. So where's the slope positive? Well, slope is positive between 3 and 6. If you look at the graph, slope is sloping up between 3 and 6. So acceleration is positive from 3 to 6. And actually, it doesn't look like it's positive anywhere else. So that would be the only point where the velocity, or the acceleration, I'm sorry, is positive. Negative acceleration is when slope is negative. So I have 2 points on my graph where that happens, from 1 to 2, or 0 to 2 rather. And then again from 6 to 7. And then lastly, where's acceleration 0? That happens when the slope is 0. And that happens 2 times on this graph, from 2 to 3, and then again from 7 to 9. So from 2 to 3, acceleration is 0, and in union with 7 to 9. Again, it's flat line, 0 slope is a flat horizontal line. When does the particle move at its greatest speed? Well, speed is kind of an interesting thing. Speed is the absolute value of velocity. So speed has nothing to do with direction. It could be going at its greatest speed in a negative direction, and that's going to be something you got to take into account looking at this problem. So I'm looking at the problem, I'm looking at the graph, and I'm basically just looking for the highest point. And it looks like for an instant, at time 0, and then again from 2 to 3. On the interval 2 to 3, it looks like that the speed will be at the greatest value, meaning it's furthest from the x-axis. And then lastly, what does the particle stand still for more than an instant? You might think it's standing still from 2 to 3. In fact, it's not. It's actually moving. It's just not accelerating. All right. It actually does stand still from 7 to 9. So that would be the points where the particle stands still for more than an instant. When it crosses the axis, it stands still for an instant. It just changes directions. Okay. Next question. Finding the derivative. So I chose to look at a couple questions from number 10. Looking at 10D, I need you to know that. Okay, so that'll be, if it's on the no calc part given to you or on the calculator part, you have it in your calculator, so I'm not going to have to worry about you having it. But taking the derivative of ln of cos inverse is a little tricky. And the reason it's a little tricky is because it involves chain rule, and it's kind of a complicated chain rule. So the derivative of ln of anything is 1 over what's inside the parentheses. But since what's inside the parentheses is not just x, I have to take out the derivative of cos inverse. So now I'm just stuck simplifying. So I'm going to take this. We already have the derivative of cos inverse up here, which is negative 1 over the square root of 1 minus x squared. And at this point, I can either multiply these or just combine them. But I would just say this equals negative 1 over cos inverse x times the square root of 1 minus x squared. But again, it all comes back to memorizing or putting this in your calculator. All right, the second one, B here, which actually comes before D on your packet, is a product rule. And I thought I'd look at it because it is a little bit tricky, and then it's a little bit tricky simplifying it. So the product here, so y prime or dy dx, you could write whatever form of the derivative notation you want, but it's the product rule. So it's first times the derivative of the second. Well, the first thing I'm going to do is I'm going to change this to be a 1/2 power. So if you didn't do that already, that's the easiest way to take the derivative of 2x plus 1 under a square root, is to change it to the 1/2 power. So I'm going to take 1/2, 2x plus 1 to the negative 1/2. But now I got this inside that I have to chain rule out. So I have to take into account the derivative of 2x plus 1, which is 2. So I got to say times 2. So that's the hardest part about it, because the rest is easy. So I'm going to take, that's the first times the derivative of the second, and then I'm going to do second times the derivative of the first, which is just 1. So now it's just a matter of simplifying, which is actually the reason I wanted to show this one. So now I'm going to see if I can do this. This 2 and this 1/2 cancel out, and this negative 1/2 makes it a square root on the bottom. So the first thing I do is I cancel these out, and I put this under the radical, on the bottom of the fraction in the denominator, and back under the radical. And then I say that's plus root 2x plus 1. If this is a free response question, I would say leave it, but a lot of times questions like this show up in a multiple choice format. So that's why you want to make sure you know how to simplify this at least a little bit more than you have it right now. So at this point, I can put and multiply both top and bottom of this thing by root 2x plus 1. What that's going to allow me to do is going to allow me to add these two things. And what happens when you do that is I get x over root 2x plus 1 plus root 2x plus 1 times root 2x plus 1. If you look at this, that's just going to be equal to 2x plus 1. And on the bottom, I get over root 2x plus 1. So now you can add them because they have like denominators. So now I get y prime is equal to 3x plus 1 over root 2x plus 1. So you got to know a little bit about simplifying, combining two terms. And the other one, if you were looking at 10D, that would be the answer to 10D. Okay, so a couple little derivative rules, product rule, chain rule, all very important. Simplifying, again, on the multiple choice part of the test, definitely going to be important because you might not get an answer that looks like something that you get, so you need to know how to simplify it down. All right, number 14 I chose to look at. All right, so looking at this one. How do you determine what x values make that graph, the tangents to the graph vertical, and what x values make the tangents to the graph horizontal. So looking at this one, it's actually real easy. If it's vertical, then I know that dy dx is undefined. Well, what makes dy dx undefined is simply setting the bottom equal to 0. So if you take the bottom of dy dx, the fraction, it would be undefined. So if the bottom equals 0, then the graph is undefined. So I'm going to solve this equation for x. So I could take out a 4x. I'm left with x minus, not minus 16, x minus 4 equals 0. So then the zero products property tells me x equals 0 or x equals 4. So values of x that make the derivative undefined are 0 and 4. On the same note, values of x that make the tangent lines horizontal at those points is when the top. So if dy dx is going to equal 0, then I'm going to set the top equal to 0. When you do that, really quickly you get x as a half. So that was just kind of a review of horizontal tangent lines versus vertical. When you have dy dx, you could set the bottom equal to 0 to make tangent lines undefined slope, or top equal to 0 to make the tangent lines have horizontal, or make the tangent lines horizontal and have 0 slope. All right, d squared y dx squared. This is a notation that trips up a lot of people, but essentially it's y double prime. And if you remember that, then you know that this one is just a matter of finding y double prime. So I'm going to try to do that. And first things first, this is a chain rule question, so I'm going to work my way outside in. So all I did there was the power rule. So something to the negative 1/2 becomes negative 1/2. Something to the negative 3/2, you subtract 1 from the power. But now I got to take into account the fact that I got to take the derivative of what's inside. All right, so I showed that step. That's actually a really easy derivative that would just equal 2. But it's important to note. So then 2 times negative 1/2 should cancel out the 2 and make it negative. So then altogether, I should get negative 2x plus 5 to the negative 3 over 2. So there's y prime. Well, I didn't want y prime. I wanted essentially y double prime, d squared y dx squared. So I'm going to do the power rule again, do the chain rule again, and take this down. So I'm going to say 3/2. When you multiply out front, 2x plus 5 to the negative 5/2. Still subtract another 1. Now it's times the derivative of what's inside again, which once again is just 2. So kind of an easy one if you know the notation, what it means. But once again, if you multiply 2 times 3 over 2, y double prime ends up equaling 3 times 2x plus 5 to the negative 5 over 2. If you wanted to rewrite that with radicals, that would be equivalent to 3 on top, and then you got the square root of 2x plus 5 to the 5th power. All right, and that would be equivalent in radical form. So either way is acceptable, but that's how you would do the second derivative. So just a couple tips there, making sure chain rule, making sure you do all those things. All right, now we get into these questions where it's related rates. So with this question and with the next one, I'm going to look at 23. The idea is that you need to find out how to relate the rates. So essentially, it says find the rates at which the box's volume A and surface area are changing at the instant when x is 4, y is 3, and z is 2. And they also give us this and this and this. So these are the important parts of this problem. So then I'm going to look and I'm going to say, first thing, A, how is the volume changing? Well, if I want to find how the volume is changing, I'm going to say, what is dV dt? What is the rate of change of the volume with respect to time? So right here, the volume of the box is x, y, z. So I want to take dV dt. Well, the derivative of x, y, z with respect to t is a little bit tricky, and it involves the product rule. So I'm going to say xy times the derivative of z plus z times the derivative of xy. Well, the derivative of xy is going to be x times the derivative of y plus y times the derivative of x. Sorry, I put dx on the bottom here. I should change that. dt. These are all with respect to t. So altogether, you get xy dz dt plus xz dy dt plus zy dx dt. And now it's just a matter of plugging everything in. So hopefully that helps you. Now you just take and plug in everything, and you should get what dv dt equals, which is in the back of your answer sheet. The other problem, you want to find the rate of change of the surface area. So in that case, I need an equation for the surface area of a box. Once again, I got 6 sides to a box. Each side has an area of 1, x times y, or y times z, or x times z. So here's your surface area model. And now I want to find ds dt, the derivative of the surface area with respect to time. And I need the derivative of this. So each one of these is its own product rule. So it's kind of a lot of work. So it's going to be 2 first times the derivative of the second plus second times the derivative of the first plus 2 first times the derivative of the second, so y times dz dt plus z times dy dt plus 2 x times dz dt plus z times dx dt. All right, so then you expand that all out, combine your like terms and everything that you see there. So essentially ds dt amounts to 2x dy dt, 2x dy dt plus 2y dx dt. I kept writing dx there, so all dt's, it's just kind of a habit of writing it. And then you got 2y dz dt plus 2z dy dt plus 2x dz dt plus 2z dx dt. All right, and once again, at this point, you would plug in everything that you know, and you got all your values up at the top. I would plug in all the x's for x's and all the z's for z's and all the dx's, dx dt, dy dt, and dz dt's, and you would get your answer. Again, is in the back of the answer sheet. Hope this helps, and hopefully you can do a little better on your test because of this video. Thanks.